overview of the high-dimensional data algorithms and complex data. And the first speaker is Arnold Filter.
Thank you for coming. And let me just warn you that this is a long talk. Bear with me, and we'll make it. So I will talk about path decompositions, which are space partitions, very useful for various algorithms, and minor-free. And I know most of you don't work here on minor-free graphs. However, the minor-free part of this talk is very minor. So don't be discouraged by that, and we'll learn about path decomposition and see how the tracking skeletons are coming to play. So what is a stochastic decomposition? It's basically a partition, a random partition of our metric space, such that every cluster and every partition has small diameter, and we want that nearby vertices will be likely clustered together. And once you have such a distribution, is very useful for divide and conquer and many other algorithms. So let's define it formally. Given a metric space X or a weighted graph, the same thing. For us, a distribution over partitions called beta, delta, path decomposition, so two parameters, beta and delta, if first, every cluster is of diameter at most delta in every partition. And secondly, if for every small enough parameter, gamma, and every point z, the ball of radius gamma times delta, that is gamma fraction of the allowed diameter delta around the point z, is contained in a single cluster with probability which is proportional to this gamma. Here is exponential in minus beta gamma. Or another way to think about it, the probability that you cut the ball is bounded by beta times gamma. Okay, so beta is called the padding parameter, and you can see that for small gammas, the probability should be smaller, and as gamma increase, the fraction increase, and the ball increase, we allow the probability to increase as well, to cut the ball. And if you can do such a partition for every parameter delta, then we say that the metric space admits a beta path decomposition scheme. So usually we will not care about delta, and beta is the important parameter, the padding parameter. Another way to think about the padding parameter is to say that there is some partition into clusters of diameter delta, such that every ball of radius delta over the padding parameter is contained in a single cluster with constant probability. So we kind of can say this size of balls with constant probability. And that has numerous applications. It's a very basic tool, and arguably one of the most important properties of metric space is its padding parameter, and I will not attempt going over this numerous list of applications. So what do we know about padding parameters? So back in 1996, Bartal showed that every metric space admits a log n padding parameter log n, where n is the cardinality of the metric space. That is, you have some partition for every metric space such that balls of radius delta over log n are contained in a single cluster with constant probability. And this is also tight, as Bartal showed, just by looking at the expander. If you partition expander into diameters which are slightly smaller than the diameter of the expander, you will cut half of the edges, and that's that. But you must, you cannot save larger, have larger probability here. So let's go over Bartal classic algorithms. It will be useful for us as well. So the algorithm is greedy and quite simple. It orders the points arbitrarily, and for every point, so the first point, it samples some radius Ri, and then it creates a ball of radius R1 around X1. And then here R1, so we sample it using exponential distribution with just mean 1, but then we scale according to the diameter we want to get eventually. So we'll scale it by delta, which is the target diameter, the maximum, divided by log n. And then the first cluster will be all the points at distance R1 tilde around the first point. Then we go for the second point, sample again, independently, getting some new cluster. And we continue, so on, so and so forth. So we can even choose centers which already been clustered. And it takes all the points at distance at most R3, which are not yet clustered. So that's that. So first one can observe that with high probability, all the sampled radiuses will be of size at most log n. And if this didn't happen, then the diameter of every cluster will be at most delta. So with high probability, we get the diameter guarantee. Let's see that it actually have the padding that we promised. So consider some ball of radius gamma delta around the point Z. What's the probability that it's contained in a single cluster? So the way to analyze it, we kind of think of growing this cluster as a continuous process. When the exponential distribution behaves kind of geometric distribution, and you grow it until the first time that some ball cluster the first point in the ball around Z. And now, if it will continue, it continues to increases. If it will stop increasing before increasing diameter of this ball amount, then the ball will be cut. And if it will increase at least the diameter amount, then the ball will be clustered. And now, because of memoryless, we know that the probability that it will increase by increased diameter is exactly as just if Ri will be larger than diameter. And this is just e to the minus gamma and log n here, which is our scaling parameter. So overall, we got exactly what we wanted here. This is the padding parameter of this decomposition. Okay, so, so this is the easiest way I know how to construct a padding decomposition. However, actually, Bertal used something slightly different. Bertal used truncated exponential distribution. And truncated exponential distribution is simply an exponential distribution conditioned on the fact that all the radiuses will get a value which is the maximum we allow. So we don't know anybody to go beyond this. So this slightly changes the analysis, or maybe there are some integrals involved. It's a bit messy, but it still goes through. So it's good enough to use this truncated exponential distribution, and it's important kind of that the parameter that you use here will be numbers. However, now with truncated exponential distribution, we have a nice property, which is some type of locality. And specifically, if you look from the point view of the point Z, vertices or centers which are very, very far or farther than delta away have zero probability to cluster me or cut the ball because they're too far and the radius will never be that much. Right? So we kind of say that only this is the area where the centers have non-zero probability to cut the ball and cause the bad event. And we'll call them threateners. They threaten me, they threaten to cut the ball. While all the other centers are non-threateners. And they're nice. And as a rule of thumb, usually you can prove that the padding parameter is simply log of the number of threateners. And let me formalize what I mean by this. So this is a result from 6 years ago, which says that if you have a sparse net, then you can construct a padded decomposition. So how it goes, suppose that you have a net, which is a collection of centers, such that for every vertex x, there is some center at distance delta, for each one of them. And in addition, this set is sparse in the following sense. If you look for every ball, for every center on the ball of radius 3 delta, you will see at most tau net points. So if you have these two properties, then you can prove that this metric space admits a padding parameter log tau. Is for this for some specific delta. And the idea is that they are threateners, and you basically can run the same Bertal's algorithm with the only change that now you condition on them being at most log tau and not log n, but the analysis still goes through in the same way. And actually, you can even go more. You can push it further, and you can say that suppose that they have only small gap. So the closest one is distance delta. And if I go a bit farther away, to say distance 1 plus eta delta, then I see some bounded number of centers. So even this is enough to get padding decomposition. However, now we need to scale by eta as well. So the padding parameter will be linear more than eta, but still logarithmic in the sparsity.
Two questions actually. One is how to show the diameter guarantee with the original exponential.
You just showed with high probability. Yeah.
But then you have to repeat.
Right. Or just say that I found them quickly. There's some different options.
Okay.
Okay, so this is what I want to say about general metric spaces. And now we will slowly go into minor free graphs. So let me remind you what minor free, in case you didn't see it for a while. So we say that the graph H is a minor of G if it can be formed from G by a series of the following three operations: deleting edges, deleting vertices, and contracting edges. That is, taking two vertices, making into one vertex, and keeping all their neighbors. So if you take any graph and continuously do one of these three operations, you'll get a minor. And the famous Wagner-Kuratowski theorem states that a graph is planar if and only if it does not contain as a minor K5 or K33. You can think, for example, that our roads in the real world, they kind of not really planar. There's some bridges, there's some canals, some stuff happened, but not a lot. It's maybe not planar, but it's almost. One way to catch it, say it's minor free. In general, there are big study about this family of topologically restricted graphs. And another thing to know about the minor free graphs is that they have the scary structure theorem, which says that there is some complicated way to break minor free graph into smaller and simpler components. However, it hides portable constants. And the nice thing about path decomposition is that they don't go through this scary structure theorem, and they use only minimally the properties of minor free graphs, as we soon see. So the first result about path decomposition for minor free graphs was by Klein, Plotkin, and Rao, who showed that graph excluding KR admit padding parameter RQ. This was a beautiful result. It was a beautiful partition. And let's recall that we know that for general metric spaces, Bartal showed that any n vertex, there is some n vertex graph with padding parameter log n. So if you just take this graph with R vertices, you'll get that there is some R vertex graph with padding parameter log R. But obviously this graph is KR minor free, and therefore there's a lower bound on the padding parameter of minor free graphs of log R. And so we have here an exponential gap between upper and lower bounds. So there's been a lot of work on the minor free graphs and some related families, specifically for Kashiropoulos and Talwar improved the same algorithm to R square, and then Abraham and Anupam Nazars came with the beautiful Capps and Roberts algorithm that we discussed in detail and get parameter R. And there was still the gap remained for 30 years between the polynomial and logarithmic. And the main contribution of this work is to finally close this gap and to get the logarithmic padding parameter for minor free graphs. Okay, so before we go to see how this works, we'll begin by recalling the Capps and Roberts algorithm by Abraham et al. So this is an algorithm that you can run on any graph, and it works as follows. So it's very similar to the Bartal algorithm, but with a small twist. So we begin with first arbitrary vertex, and you sample some radius in the same way, and the cluster is all the vertices distance most the R1 for your sample. Next, you pick another arbitrary point, and you add the shortest path from your point to the previously created cluster. And this thing is called the skeleton. And now you grow a ball around the skeleton. And this new cluster, we'll call it supercluster. And then third step, we take the third point and we connect it, and we add a shortest path tree to all the previously created clusters. And we grow a ball around the skeleton. This is the third supernode. And on the fourth one, again, we add shortest path tree to all the previously created clusters and grow a tree around that. But now there are several connected components.
Excuse me, when you say shortest path tree, are you using the picture? You just add the shortest path to each one separately.
Right.
Is this what you mean?
Right. Yeah.
It's like a start, not a start.
No, but I mean, it might, maybe break here.
I could break.
Yeah, but it should be there should be no cycle.
If you don't show this path to different targets and you use the same type breaking rule,
It will be a
it
tree.
will be a trick.
Yeah, no, I understand this. No, I was just imagining from the picture.
I think there will be some examples when.
In your picture, it's a star.
Yeah.
Sorry, are you making a shortest path tree to one, like, distinguished node in each cluster? Or
No, to the closest one.
Every node, the closest one, so just one leaf per cluster, not.
Right. Well, it might be more if for some reason you have another cluster that requires that specific leaf, but
Okay, sure, but you don't need to connect to all of them.
Right. In particular, the number of leaves in the tree is equal to the number of clusters you can see. And now the next cluster, X5, he cannot reach the fourth cluster because it's a different connected component. So he lives only in this connected component. So he'll build his skeleton tree only towards the clusters that he can reach. And grow a ball here. And exactly the next one, see there's still stars really. He can see only two clusters, no, actually three, also here. So he grows ball around. So the skeleton shows battery to all of them, and so on and so forth. And you continue until you
This is
decompose.
ChatGPT.
No, this is me. So, and so here's like one key observation is that if you can run any graph, but if it so happens that your graph is kr minus 3, the maximum number of leaves that you can see is at most r, or actually r minus 2. And why is that? So suppose I created a cluster 5, and I can reach 3 and 2. It means that 3 and 2 are connected between them, because when 3 was created, he also could reach 2. In particular, all the clusters that I can see are all connected between them. So if you will contract me and all the clusters I can see, you'll get a minor of the size of the number of clusters plus 1. So therefore, if I'm kr minus 3, the maximum number of clusters I can see at any point is at most r minus 2. This is the only property we will be using.
Is it clear each of them can see like connected to the others?
Yes, because think that there is some connected component which was larger when my ancestor was created. And if I can reach my other ancestor, then he also could have reached my other ancestor, so he will definitely choose to do so.
And then it will go through this white space.
Exactly. And the main result in the Abraham et al. Paper was that this process has padding properties. Specifically, so this is a padding partition, I guess. And specifically what I mean is that if you sample partition to supernodes in this way, then for every center Z and diameter and parameter gamma small enough, the ball of radius gamma delta around Z is contained in a single cluster with probability at least e to the minus order r times gamma. Or in other words, this is what we call padding parameter r. However, this is not really pi decomposition. Why? Right, the diameter is unbounded. And this length here could be completely unbounded. So the diameter is not bounded. So why do we do it? So the advantage in this decomposition is this: the supernodes are not general minor free graphs. They are much more structured. And specifically, consider a supernode. So this is just the shortest path tree with at most r leaves. So we can simply add a sparse net here. So we can for every path, there are k of them, add a net distance delta from each other, and now this sparse net. From one hand, every point is close to one of them, and if you increase the ball, the number of threateners from each path, because it's the shortest path, so you cannot see a lot of them. Only a constant number will be contributing only a constant number of threateners, and overall will be only r threateners. So we have a sparse net with parameters delta and sparsity order r. And therefore, by using this black box, sparse nets imply padding decomposition, we get that the supernodes we can partition well with padding parameter log tau, or here log r. Right? So,
Okay. Here is something that I didn't get. So you said that any point like the blue one is close to one of the red ones.
right. Because this is a ball around this skeleton. So you must be close to the skeleton, right? It's like you're close to the center of the ball. This bold green thingy is the center of the ball. So every point in the ball is close to the center in this sense.
This green area is only it's only the area around
Right.
the spots.
This is a ball around the skeleton. Like here, right? It's all balls around the skeleton.
Yeah, sure. I was thinking it was the entire area includes.
No, it's only the supernode. And yeah, the supernode has a sparse net, and therefore supernodes by themselves have admit padding parameter log R, log the number of transistors. And now you can compose these two partitions. First, partition to supernodes, then partition each supernode, and you'll get that the probability to get a ball is a maximum of them, which is order R padding parameter. So this is basically recovering Abraham tau. And you can see the bottleneck here is the first part, this order R. While this is right, this is the correct answer for this type of supernodes. So we need to improve, maybe improve the analysis of Abraham tau to show its log R. And I was stuck on this for many, many years, or the solution eventually is different. So to show you, so the roadmap to get our solution, there's two main tools that will show you. So to get the log R padding parameter, first is the meta theorem, reducing from sparse covers to padded decomposition. So we soon talk about what sparse covers, and we'll show that it's enough to prove that you have a sparse cover to get a padded decomposition. And the second thing will be just to construct better sparse covers. Ideas. So this reduction actually will just go through this sparse net argument, sparse net implied padded decomposition, while the better sparse covers will use a new very heavy hammer called buffer cup decomposition by Chang et al.
So the reverse of this padded decomposition as sparse cover is straightforward, right?
Yeah, but you're paying log n factor. Yeah. Okay. So let's talk about sparse covers. So sparse cover, in some sense, it's the dual notion of pi decomposition. In pi decomposition, it's a distribution over partitions when you want each ball to be covered with some probability. A sparse cover, on the other hand, is like a deterministic thing in nature. It's just a bunch of clusters. They could intersect. And the goal is that every ball will be contained in some cluster, while every point will be contained in a small number of clusters. So formally, there's again three parameters here: rho, tau, and delta. Say that the metric space is rho, tau, delta have sparse cover if you have a collection of clusters, all of diameter at most delta, and such that every ball of radius delta over rho, so every rho fraction of this diameter delta, is fully contained in some cluster. So this green ball here is fully contained in this blue cluster, and this one is fully contained in this red cluster. And the final property is that it's sparse, and that is every vertex contains at most tau clusters. This one containing two clusters. And as previously, if you can do it for every parameter delta, then we said that you have sparse cover scheme. So the important parameters here are the rho, which you can maybe call padding, and tau, which is the sparsity. Yeah, so this is the notion, this padded decomposition, distribution over partitions, delta bounded partitions, just every ball is contained cluster with some probability, and sparse cover, it's again a collection of clusters of diameter delta, such that every ball of the specific radius is contained in some cluster, and every vertex contains small number of clusters. And as Yasemin said, indeed, one can observe that one can simply sample many padded decomposition to get a sparse cover. Specifically, if you sample the inverse of this probability padded decompositions times log n, every ball will be happy, it's one of them, and therefore you will get a sparse cover with parameters of this gamma here, and the sparsity will be just the inverse times log n. And the challenge usually is to remove this dependency on n. Right? So some special graph families want to show that regardless of cardinality, you can construct good sparse covers. And there was a lot of work on sparse covers, starting with Avram Peleg in the early 90s, and going to even this year when we get the best known padding sparse covers for monofree graphs. So you should really have constant padding and exponential sparsity. This is the last result for this paper. And the theorem that we'll prove in a second is that if you have sparse cover with parameters rho and tau, then you have padded decomposition, which is linear in the padding rho and logarithmic in the sparsity tau. And if you take this theorem and apply it on the best known very recent sparse cover, then you can recover R padding parameter from monofree graphs. So this is already known. But yeah. different way.
Your inverse relation from padding decomposition to sparse cover,
I mean, there is with a log.
the log.
I don't know where it is. Okay, so our plan. So in this work, we improved sparse cover with constant padding and polynomial sparsity, and now using the meta theorem, we get our main result, which is padding parameter log r.
The first theorem, should I think of some, I got some multiplicative weights and then samples from it?
I'll show you. It's not sparse net argument basically.
Those sparse coverage are not already based on pattern decomposition.
So many constructions of sparse cover were based on padding decomposition.
But this
But
was,
but here, like the thing is that this algorithm by Abraham et al. Was like padding decomposition. You can use it for sparse cover with a log n, and we're trying to improve the padding parameter there directly without success for a decade. And this kind of idea of doing sparse covers instead kind of was a game changer in the sense because sparse cover are much more forgiving. You can make some mistakes and still go through.
so
Here,
for those ones.
I mean.
The results.
I mean, they say this is tight, probably up to 200 years conjecture or something. And so if you replace n by r here, it will hold.
But what about the table?
No, that's what I'm saying. You take like usually the lower bounds focus follows. You take your general graph lower bound, you replace n by r. This is a line of free lower bound. I don't know anything beyond that. Which might be tight as all right. I mean, if you want a constant, this should be like r. So you cannot get below constant in r. So it have to be polynomial, but which polynomial? Yeah, it's probably not the right one. So our plan is first to see this meta theorem, and then to discuss how one can construct better sparse covers. Then we'll happily conclude the main theorem. Okay, so this is the reduction, which is surprisingly simple. So consider your sparse cover. So these the points are the graphs, and this is the clusters. And what we'll do, we construct auxiliary graph, and we sample a pi decomposition in the auxiliary graph. And this is constructed as follows. So for every cluster, we add auxiliary nodes. So for every cluster C, add auxiliary node XC with edges to all the nodes in the cluster. And now this is the first cluster, second one, and so on. You do it for all the clusters. Now the smart thing here is how to define the weights, these edges. So the diameter, recall it's delta, and the weight of each edge will be twice the diameter, 2 delta, minus distance to the boundary. That is minus distance to the closest vertex, not in the side, not in the cluster. So this vertex here, for example, is very close to the boundary. So the weight of this edge will be 2 delta minus 1. Well, this vertex here is far from the boundary. So the weight of the edge will be 2 delta minus 4. This unweighted case. And now observe that we have two problems.
Let's slow you down for a second. Could you do that one? Could you explain what's happening?
You're looking at the red cluster or the blue cluster?
Yeah.
Oh, here,
Yeah.
no, here is this red cluster with this vertex as a center. So look on this vertex, part of the red cluster. So the edge, weight of the edge from this vertex to the cluster center is twice diameter, not of the clusters, like just delta, the global parameter, minus distance to the boundary. It has a neighbor in the boundary. The distance to the boundary here is 1. While this vertex here, U, has distance to the boundary 4. So the weight of the edge will be 2 delta minus 4.
The weight of what edge?
Between the vertex to the auxiliary cluster center.
So you've taken every component, you've added a vertex on top, it's an apex of some kind, and then.
Right, and you can think it's kind of it's closer to the center and farther as you go close to the boundary.
You just go one cluster.
You do it for every cluster.
It's like this star.
So for every such, I mean, you do this star above each cluster and this is the way you define the weights.
The weights are between delta.
Right. I mean, if it's connected. And so here's first observation. So for every vertex Z, this is a sparse cover. So there is some cluster when it's covered, which means that the entire ball of radius delta over rho is contained in this cluster. And therefore, the distance to the boundary is at least delta over rho. And hence, the weight of the edge will be at most 2 delta minus delta over rho. So this is kind of my closed center. Now, next, I argue that every center of a cluster that don't contain Z is a distance at least 2 delta. Indeed, consider some center cluster, say XC, which is not containing Z, right? So Z is containing this small red one and big blue, but not in this red one. So what's the distance between Z and XC? There's no edge. So we must go through some vertex in this cluster. So suppose the shortest path from Z to XC goes through Y. So what will happen? First, I need to go from XC to Y, and then from Y to Z. How much I will pay for this edge from XC to Y? I will pay 2 delta minus distance to the boundary of Y, plus distance from Y to Z. Distance from Y to Z is at least as large as distance to the boundary. So Z is some vertex out of the cluster, and this is the smallest distance. So therefore, they cancel out, or there's an inequality here, and we get the distance from Z to XC is at least 2 delta. So the conclusion is that we are distant at least 2 delta from every auxiliary vertex, representing a cluster we're not in. And because each vertex belongs only to tau clusters, as this is a sparse partition, we obtain that there are at most 2 delta auxiliary vertices. Auxiliary vertex is a distance 2 delta. At most tau, such vertices. Now it's the time to apply the same theorem we used, that sparse nets imply by decomposition. Right, so the theorem was that, so here the gap is very small, 1 over rho over delta, between close and far. But this is enough. So basically, if you have a gap, if you have sparsity tau here, and gap of eta, then you have a padding parameter 1 over eta times log tau. So let's put our parameters. We have the closest center distance 2 delta minus 1 over rho delta, and at most tau distance 2 delta. So therefore, our padding parameter will be linear in this rho times log tau. This is the theorem from sparse covers to padding.
The centers, they're not in the original graph.
Right, you can show that the centers don't shortcut anything. Things that go between centers and back, at least to deltas, they don't help you. So yeah, you just remove this, you forget about it.
But all this is for weak now.
Right. Then the result is for weak now.
If I give you the partial that you gave was only for weak now.
Right. But I mean, specifically, this theorem we know how to prove is strong diameter, but the auxiliary vertices breaks it here. I mean, if you use here MPX, it gives you strong diameter.
After the partial is also.
Okay, so this was the first part. Sparse covers imply pi decomposition. And now we go to the main contribution, that there are very sparse covers with polynomial sparsity. And to prove that, so this goes, this is based on cup decomposition. Round it out with some additional properties, but first let's recall this cup decomposition. So basically what we'll do, we partition to supernodes instead of clusters. But as I said, for pi decomposition, supernodes are good enough. They're also good enough for sparse covers. And the reason is that every supernode contains a good sparse cover. Simply take a net around each shortest path tree and add a ball around each cluster, and this is a sparse cover because every vertex will be covered, and you can be covered with only constant number of vertices per path, or there are walls. So it will be enough to cover supernodes, and you'll pay additional R factor in the sparsity. Okay, so now let's discuss the cup decomposition and the additional property we'll need. So one way to look on cup decomposition is like a tree construction. So the first cluster is the root of the tree, and then the second cluster is a child of the root, and the third one is the child of the second one. And now we have two connected components, the inside and the outside. So we create two clusters, which are now siblings, right? Because they are not created from each other, they're not related. So they both are children of the third cluster. And now there are 5 connected components, so we'll create 5 different clusters, and they are children of the last supernode created in their connected component, and so on and so forth. So now we have this tree over the supernodes and their relations of ancestors and descendants. And we also say that 2 supernodes are neighbors if they're attached. When the descendant was created, he added like its tree, it reached the ancestor. And like here's observation, we observed it previously. So suppose that you have supernode eta with 2 ancestors, eta prime and eta double prime, such that they are both neighbors. So like here, 12, it's 12. This is 12, and this is indeed touches 3 and 8. No, so 3 and 6. And they are indeed neighbors between them. So if I have 2 ancestors, which are both my neighbors, they must be also neighbors between them. And this is the reason that I might have at most R neighboring ancestors. Because if I contract all the neighboring ancestors, I will get a minor. Okay.
How is the neighborhood reflected that field?
So the neighborhood, so here I wrote, this tree doesn't reflect the neighborhood, this is just the ancestry, but it's I guess too small to see, but for each supernode I wrote here all the ancestor supernodes, which are neighbors. And there are at most R of them. Property. So Chang, Conroy, Lee, Milinkovic, Solomon, and Tan constructed a cup decomposition with an additional buffer property. So this was a real breakthrough 1 year ago. Gave many different applications, tree covers, and standard point removal, distance oracles, and also the main working tool for this result. And this is the deterministic construction of cup decomposition. So originally, cup decomposition was a random process, such that small balls contained in a single cluster with some probability. Now there is no probability involved; it's just deterministic. But so there's no covers and can cut whatever. However, there's additional buffer property. And what this buffer property means? That for every 2 supernodes, such that so consider 2 supernodes eta and eta prime, such that eta prime is ancestor of eta, but they are not neighbors. Like for example, 4 and 16 here. So 16 is descendant of 4, but they're not neighbors, they're not region. So in this case, the cup decomposition of Chang et al. Guarantees you that the distance from eta to eta prime is at least delta over R. Now there's some buffer, some gap between them. They could not be arbitrarily close. And the distance is computed in the connected component where the ancestor was created. So think of the time when we created 4. So this was the connected component, or another way to think of it, this connected component contains all the vertices in the supernodes in the subtree rooted at 4. So we created some supernode here, and the guarantee is the distance to 16 that was created later, not touching me, is at least delta over R. And this turns out to be super crucial property. And actually now, you already have a way to construct an easy sparse cover. And here's how. You can simply take every supernode and, oh, sorry. So here one observation. Because of this buffer property, the number of ancestor supernodes at distance delta is only exponential. So if you look on some supernode, and you look at all the ancestors, those who touch, this is 0, those who don't touch, number of ancestors at distance most delta is only exponential in R. So it cannot be arbitrary. This is because it's buffer.
each time you get to somebody you cannot touch, you kind of have some buffer, and then when you get to somebody that he cannot touch, it decreases. And overall, it's only an exponential number of supernodes. And using this observation, you can construct a sparse cover very easily. Simply take every supernode and create a ball around the supernode at the cluster where it was at the connected component where it was created. So here, for example, we go over 4 and we grow a ball around 4. But note that this ball is in the connected component of 4, so he cannot touch 3. And he cannot touch 5. It's different subtree. But he can touch everything in its subtree. And so on. This is like a ball around 8. So he cannot touch anything that was created before him, but he can touch this tree. So this will simply be my clusters for the sparse cover. And let's see. So this is sparse. Why? Because each vertex would join only supernodes at distance most delta. Only ancestor supernodes, and there are only exponential number of those from the one. On the other hand, this is also a cover. Why? Look on some small ball here, and look on the first time where some vertex joined to some cluster. So this first time, all the vertices, like supernode, I mean the real supernode. At this time, all the ball vertices in the ball are still available. And because we created large enough ball around the cluster, then we will cover this entirety. So we get both sparsity and cover. Right, so we get constant sparsity and constant cover and exponential sparsity. And the question is how to get this thing to be a polynomial. What we need for our main result. Okay, so bear with me. So now we created, so this is like our buffer cup decomposition, and this is the graph of relations. So we add an edge between any two supernodes, which are neighbors. And this is like the big picture. Now maybe you can see these numbers. And the observation is this, this tree has small tree width. If you don't know exactly what tree width is, just ignore it. It has all the properties that this construction has. But basically, I mean, and this is the bag. So for each, so the tree decomposition is exactly this one, and the bag of each supernode is all the supernodes that it can touch at a time. And the natural approach for graphs with small tree width is divide and conquer. So simply, you can take some bag, take care of all the supernodes in this bag, and continue on every remaining component. So specifically, take a centroid, and for every supernode in the bag of the centroid, create a ball, radius order delta. So I take this third to be my centroid because it will break the graph nicely. Now I create a supernode around first, supernode around second, and supernode around a ball around third. And now delete this third supernode and continue recursively on each one of the clusters. So this looks promising. However, it does not work. That's an issue. And the issue is that it's not a cover. So this is the picture that I want you to look about. So this is my centroid, the supernode I chose to delete, X. And its bags is X and X prime. And once I will delete X, it will break to the ancestors of this and their children, which is T1, and two children of X, T2 and T3. And at this time, I created a ball around X, this brown ball here, and the ball around X prime, which is the purple ball here. And I create these clusters. Now I plan to recurse on each of these three parts. However, you might have a ball which starts above X prime and ends up below X prime. But X prime doesn't have any promised size or anything like that. And so this ball will not be taken care of now. And once you recurse, then the vertices of this ball break into different components, so you'll never take care of it. And the solution is to use active vertices in a sense. Each vertex, instead of going with the recursion with the supernodes it belongs to, it will go to some other supernode. So it will try to go above in the tree. Specifically, it will say that a vertex V will be associated with the first supernode
first with respect to tree order, a distance most to delta. So for example, this supernode here is distance to delta from the fourth supernode, so it will be associated with the fourth one. While this is associated with the sixth, so it will go with the sixth, this one with the 8, and this one with the 17. And when you recurse, you'll send each vertex to the supernode it is associated with, or its subtree of this supernode. Now the picture will look like this. So even though X prime and X and here, they have some further impact on nodes below them, which will recurse on them. And once you have this property, you have the lemma that says that for every ball, either it being taken care of now, or it continue as one unit together to one of the recursion. So here, this ball was not taken care of now, but will go together with the recursion of the green part, while this ball here is broken, but it's fine because it's taken care now. And for this, you only need to increase this to be 4 delta instead of 2 delta. So this is how we solve the first problem. So, and once you have this lemma, you will eventually get the cover by induction. So what you get overall, we get a sparse cover. However, the depth of this recursion is log n. And this is a problem, it's not what we wanted. So overall, you'll get a sparse cover with sparsity r log n. Okay, so how should we break this log n? We need to have some much smaller recursion tree. And the solution is instead of deleting only the centroid, we need to delete many different supernodes at the same time. So this is the picture. So this is the tree decomposition or the tree structure of the supernodes. And previously, I just chose this one to be the centroid, because it breaks the graph nicely. But this was not enough, because the depth was log n. So what do I do now? Now it shows what to delete greedily. I start with the first supernode, I will delete you. And now I go down in the tree, and for every, they mark all the supernodes in this tree, in this bag as well. So here's just the first one. Now for each supernode, which doesn't have a marked supernode in its bag, I will decide to delete this supernode and to mark all the supernodes in its bag. So you see, like this is not chosen, this not chosen because they contain one, not chosen, not chosen. Now all of this does not contain one, so they are all chosen. And all the supernodes in their bags are marked. And now I continue. So all this, the gray one not chosen, while this one contained 2, 3, 4, and 6. It continues on here, but when I got to 27, none of them is in my bag. So again, 27 will be chosen, and all these ones will be marked.
So like an independent set or something.
It's kind of an independent set. Yeah. And now the algorithm is as follows. Create a wall for this 4 delta around any marked supernode. Delete all the chosen supernodes, not the marked supernode, but the chosen. So I delete the 6, but I don't delete this 2, 3, and whatever. So only when you chosen like a bag, you delete the supernode representing this bag. You mark the others, but the deletion is only the one that you picked. And then you will recurse on every remaining connected component, but of course with respect to the active vertices. Okay, go with the first supernode, the distance most to them. So this lemma still goes through. So you either take care now, or go together the single leg of the recursion. So you still get the cover. And the question is, what is the sparsity of the cover? So let's look. How much do you pay in a single step of the cover, and what is the depth of the cover? So first, let's see how much you pay in a single step of this cover. So consider some vertex belonging to this supernode or somewhere below here. You can be clustered only by your ancestors, because every vertex, every supernode which is non-ancestor will not touch you at all. And so this is all my ancestors, and I might be clustered by like all the marked vertices here. A distance most delta. So this is the same. Yeah. So the question is, how many of them are a distance delta from them? So this is the picture. Your vertex belongs to eta, which so it's not marked. And now it has some ancestors. This is the first marked chosen bag centered at the eta 1 with bag x1. Then this is ancestor, which is not chosen. It has some marked vertices, but it's not chosen. And this is the second chosen ancestor. So there are some things happening in between, which bag x2 and so on. This is the k chosen ancestor with bag xk. And now eta is not neighbor of any supernode in the bag of eta2. Why is that? Because I know that if I have a neighbor here, then eta1 will also have a neighbor here. But I chose eta1, which means that it initially doesn't have any marked node in its bag. Therefore, I have no neighbors here. So the distance from this supernode eta to every supernode in the bag of eta2 is at least delta over r. This is the buffer you get by Chang-et al. And now you can pop it up and say that if you look I steps above, then the distance will be at least I times delta over r. So after r such steps, you will start being covered. And overall, there are at most r chosen bags, a distance order delta from eta, and each such bag contains r supernode that can't touch me. So overall, in a single level of this algorithm, the number of supernodes that it could cluster me are only r squared. The second question is how many levels are there? So now that we kind of pick the first one, and then we pick each one which doesn't have anything marked, and so on. So you can see that for every supernode eta, it will be disconnected from some supernode in its bed, because either it was chosen by itself and then it's deleted, or it was not chosen. This means that it has some marked node, supernode in its bed, which it will be disconnected from. So the tree width basically decreases by 1 after each such level. So overall, after r levels will be done, and everything will be deleted. Okay, so after r levels will be done. So overall, we get only r cube supernodes containing them. And we get a sparse cover with constant sparsity and r cube, with constant spotting and r cube sparsity. And recall that it's the supernodes, so we have additional r factor from the supernodes themselves. So overall, we get the r to the 4. This is the main theorem that every kr monotony graph have a padding decomposition with factor log r. So this was the proof. I have about 10 more minutes of open questions, but I guess we can skip that.
Let's stop over questions. We'll consider it part of the research.
I want to ask a non-open question, just a question. From next to the very beginning, sort of the definition of this thing. Would you talk, because I'm not familiar with more than a couple of these applications, about sort of what's important for these? For example, is it important that I have all these parameters at every distance scale, or just on average across the distance scales? Is it important that I have distance by diameter? Would it be enough to have distance to the center?
So the diameter of this center is the factor 2.
Yeah, probably.
Yeah, so it's not, I mean, we don't get so close to the exact numbers here. So, but the other question about if it's the same scale or not. So when we talk about minor free, then basically yes, but so this log n, for example, is the worst case possible. But if you look on works like FRT or 1004, so what they showed is that it could happen, but what happened in all the scales? There's some other argument showing that if you go over all scales, that together they can kind of sum up to log n. This is the basic idea there. While the worst case is log n, on average, you
I guess that's a bit what I was fishing for. Like, is it important kind of for the applications to get it at every scale, or can I usually get by with just that on average?
depends on the application. For tree bags, for example, like FRT, was another average. Like log n was the worst case, never worse than log n. But on average, it's kind of was the locals density.
Yeah, but what's like an example of something that we need to consider at every scale?
So basically, for worst case problem, worst case guarantees. For example, universal standard tree, that's something similar to that. The worst case problem, not average. Also, the standard.
You know, Poland, well,
applications
you don't want scale, but like, you don't choose the whole alternative, like, one, you scale everything. Yeah. And, for example, I think one of these examples would be, for multi-cut. Unlike sparse, multi-cut, one scale which is usually like assumed to be one. And then you don't add up two parts, one, you need one of them. And that's the immediate one, so then that's interesting.
So I have some two remarks though before that. Sorry. So one observation is this log R is this algorithm is basically the best you can have in any graph. Even if it's not minor free, you get log n, it's still open. So you basically can say, okay, let's just run the algorithm on the graph I have. Let's forget Bertala. However, here's a question: given a graph, how do you know what for which R it's k R minus 3? This is a surprisingly hard question. The best approximation you know is square root n. However, the nice thing about this algorithm that you can run it even without, and just run it, will work.
I mean, you just need the distance, you need the graph structure.
You have the graph, you can't just run the algorithm. If it's KR3, you will get the guarantee. Or you can just try all of them, and one of them will work. So you can get this on any graph without any knowledge of the graph. You don't need to approximate the minor free. Worst case scenario will be better than you would hope for, even if it's not. This is one nice thing. Another thing I didn't talk about running time. So the running time is not very good, some polynomial. And this is because this heavy black box we used of buffered cup decomposition, which runs in some polynomial time. However, you can think about this as pre-process time. And once you pre-process and get your sparse cover, you can sample from the sparse cover very efficiently, linear time, using MPX. So in a sense, you can think of this spot decomposition. If you want to sample many partitions, then it's efficient sample just to prepare yourself for sampling. You take your sample in more time.
So it was deterministic of complete
Yeah.
composition, right? So,
Right.
but if I allow randomized construction, maybe
I don't think it will help. I mean, because you want the guarantee. If you want the guaranteed expectation, then yeah, then you need to prove it strong enough to get everything else.
still need regulated.
So currently we use just students works.
So there's like a result. So there's my result with Team Garden, but I don't remember the details. It's like a long time ago, it sort of like says that if there exists a parallel decomposition, then you can actually find then one with almost the same parameters, for example, 2 or something somewhere, like in that
Using some
polynomial time, but it requires also make an NP. So if that algorithm is polynomial time like n to the 12,
No,
then
I
maybe
think
this would be
it's not that bad. I think it's like maybe Pratik.
nothing, that could be like an approach, like you just knowing that something exists.
But they didn't write anything
You do like
explicitly.
final dual
I think they
or
told me in
something,
person.
but find one without really going through a completely avoiding this.
So open questions on the problem. So I didn't talk it, but there's like strong and weak diameter. So strong diameter is diameter. Weak diameter is just distances in the original metric. Strong diameter is induced distances. So for example, this cluster from V and U, the strong distance is 6, while the weak distance is 2. In the induced graph, so indeed the weak diameter is 4, the strong diameter is 6. It could be even more challenging for this cluster. This weak diameter is 4, the strong diameter is infinity. That's disconnected. So all the results in this paper are with respect to weak diameter. And actually there was a lot of work improving from weak to strong diameter. And this is the main open question. So we have now exponential gap for weak versus strong diameter. So we know how to get log R optimal weak diameter product position, while the strong diameter is still the R. 6 here before. And actually the same holds also for true width. So previously this year we get the log true width weak diameter, and the strong one is still this old one. So closing this exponential gap is the main question.
I guess perhaps this question again, does this matter for any of the applications?
These parameters.
No, just the distinction between strong and.
Ah, yes, yes, it matters. There are some applications. Think, for example, like routing. You want it to be strong down. Please.
Sorry, I couldn't hear, which was the application?
I mean, everything which related to routing requires it. And some batch reporting distance oracle, this type of stuff. But if you actually want the path together, it's helpful. It's also usually nicer to work with. My open question, close this gap. Same holds, by the way, for sparse covers. So our result here is with weak diameter. So we get constant padding and polynomial sparsity with weak diameter. Strong state of the art is constant and exponential. Again, exponential gap here. Yeah. And one also might want to, in padding decomposition, we usually don't care that much about the parameters, like the constants, but in sparse cover, we can't get very close to optimum, so we do care. And there's some gaps here. Here we don't know how to get 4. Here we know how to get A. Best we can hope for 2 plus epsilon. This is not an open question. Yeah, another one, this reduction actually also loses diameter. So if you get strong sparse covers, we got in our paper weak sparse covers. But even if you get me plug in strong sparse covers here, it will still give you weak padding position. So it's interesting to see if there's such meta theorem that preserving strong diameter. And here's something completely different. One of my favorite open questions now that they have no idea how to approach. So, so wake up. So this is about online pi decomposition. So consider the following input. You have some sequence of metric points arriving in an online fashion. And each time when you get the point xi, you get all the distances to the previous points that you saw. And the goal is to create a pi decomposition that once you see a point, you need to determine to which cluster it belongs. And once you chose, you cannot change your mind. And the goal is to, so we cope here with oblivious adversary. So everything is fixed in advance, but we don't know that. And to find some random partition with small padding parameter. So this was observed by Indik and Al years ago. If you just run Bertal, this algorithm is oblivious from the future. So this is actually an online thing. So for geometric, in online, you can get the optimum log n padding parameter. However, all the algorithms for like planar graphs even are very much based on the graph. So suppose that they promise you that the metric that they will show you is induced from some big planar graph, but you don't know what planar graph is. Right? So like the first point arrives, nothing about it. Now the second point arrives, it's come from this graph. You don't know about it. The distance is 3. Now the third points arrive, distance 2 to the second one, 3 to the first one, and so on. So you see the points, but you don't know the graph. And the question is if you can get anything better than general graphs or constant. All what we know, like discussing robbers, new techniques, KPR, the whole thing. So completely clueless how to approach this. We could try. That's that. Thank you.
More
For the last thing, like log n is easy, like in general. For the online version.
Just Bertal.
That's what you were asking about.
Yeah. Just vanilla Bertal works and
But about planar, you were asking about planar because
yeah.
Bertal argument works.
Yeah. Even for doubling, you can get online. This also works.
You can build the net points on the fly.
In a sense, yeah.
for sparse covers, you said that the optimal thing you can hope for padding parameter is 2 plus epsilon.
It's because of the definition. Because I care about padding balls and with diameters. So even, so even if the center is only covered is counted too. It's kind of,
Right, is there a way to redefine it so that?
maybe, but until now, they didn't really usually care about it. You can ask if you